We're on Chapter 10, Section 5, which is Learning Plan 511, Common and Natural Logs. Actually, we're going to see that these are the very good uses for logarithms, both the common and the natural logs. And then we're going to see how to use them and how to change bases. How do you use a calculator with logs? Well, what you do is you find the log key on your calculator. And so we would press log of 41,600 is 4.619, because 10 to the 4.619 is 41,600. Okay, so we could press log of 43.5, and we get 1.638. 5. I guess we're supposed to go to 4 decimal places. And then for the last one, log of 0.442, and we get negative 0.3546. Okay. So you do these two. So you'd press second function log of 115, and you get 2.0607. Log of 0.25, and you get negative 0.6021. Now, how do you use them? Well, one place that we use them is with pH. pH stands for the powers of hydronium ions. Find the pH of water with a hydronium concentration of 1.2 times 10 to the negative third. So we would say that is 0.0012. So we're just going to press log of 0.0012. Log of 0.0012, and we get negative 2.9208, which is a very acidic, that's what the log is. We have to change the sign, so it's actually positive 2.9208, which is very acidic. So pH is the negative of the log of the hydronium ion concentration. All this whole stuff here stands for hydronium ion concentration. Okay, so you do this one. So we would just press negative log 3.4 times 10 to the negative fifth. Negative log 3.4 times 10 to the negative fifth, and we get 4.46, which is acidic. Next one. Find the hydronium ion concentration if the pH is 4.6. Or in other words, since we know 4.6, that is the negative log of the hydronium ion concentration. So we would press second function log, because now we're looking for the number whose log is negative 4.6. Negative 4.6, and we get 0.000025119, or 2.51 times 10 to the negative fifth. You do this one. So 2.6 is the negative of the hydronium ion concentration. So we would say that is 10 to the negative 2.6. So on our calculator we'll press, I suppose we could just press 10 to the negative 2.6, and we get 0.00251, or 2.5 times 10 to the negative third. We also use logarithms in decibels. To measure this unit, we first assign the intensity to a very faint sound called the threshold sound, and then the number of decibels is 10 times, and that's because it's decibels, 10 times the log of the intensity divided by the intensity at that lower level. Here you see the chart that has the different decibels. And so in this equation, we would have the sound level, or the decibel level, is 10 times the log of 115 times the 115. So we would take 10 and then log of 115, and we would get decibels would be 20.6 decibels. 20.6069, something like that. You do this one. So it'd be 10 log 6.312 times 10 to the 13th. So we would press 10 log of 6.312. We can use the EE key, E to the 13th, and we get 138 decibels. Now, when would you use natural logs? Natural logs are used whenever we have a base E. E is about 2.71828 and so on. Like pi, it's a universal constant. We use it in connection with interest applications. So we have ln x, that would be the natural logarithm. The n stands for natural log. So on our calculator, we're going to use the natural log key. I don't think my calculator has a natural log key. My wife said it wasn't a very smart calculator. You'll have to press the natural log key on your calculator to calculate each of these. Yeah, I don't have those on my calculator. I can give you the answer for these three. The answer for the first one is negative 1.3471. For the second one is 2.4849. And for the third one is 5.0106. Now, where do you use natural logs? You would use them in functions such as this, and then you would just subtract this. So it'd be 51600 minus 7,457 times the ln of 700. You do this, try it, and tell me what you get. Now, according to my calculations, my textbook, it comes out to be 3,900 when you take 51,600 minus 7,457 ln 600. how do you use the change of base rule? Well, the change of base says that when you have a log base a of x, you can change the base so that this is the numerator of the fraction and this is the denominator of the fraction. Now, why does that work? Well, let's start with the log base a of x. Let's say that that is m. So then that means that a to the m is x. We know that the log base b of any number, let's say a to the m, is the log base b of the other number, x. These two are equal. Okay? Well, this is m log base b of a. If we multiply both sides by, if instead of writing m, we write log base a of x, we would have log base a of x times log base b of a is log base b of x. But we know that these two multiplied together is the same as, divide both sides by log base b of a. We get log base a of x equals log base b of x over log base b of a. So all we did was we rewrote this as m, then we substituted that back in here and divided out. So this is log base 10 of 17 over log base 10 of 3. Well, we can press that on our calculator, and we would have log of 17 divided by log of 3, and we get 2.57. Now, interestingly, we could have done the same thing and changed them both to ln 17 over ln 3. Either one would have worked. You do this one. So that's log of 60 over log of 8. So we could press log 60 divided by log 8, and we get 1.9690. Use the natural logarithms in the change of base rule and the function. I'm going to use the log base 10 because I don't have natural logs on my calculator. So I'm going to press 2014 plus 384.7 log of x over log of 2. To find the crude oil in the United States in 2008, if 1 is 1990, so this is 19. So we have 2014, because it's 19 years later, 2014 plus 384.7 times parentheses log of 19 divided by log of 2, and we get 300 3,648 million barrels, which isn't that bad compared to what they say it is.